Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Hi, how are you everyone? We are going to be talking about in lecture 25 today in our course Process Modeling and Simulation. Myself, Dr. Bassam Mohammed. We are going to talk about SNK method, and I call it SNK method. It's just the difficulty I have in the pronunciation of the names. And we have Smith method, initial slope, and slope-intercept method. And we may take also the so-called the ramp, the integrator, okay, method. So all that we have the methods that we're going to be taking today, and we are going to go through them as part of trying to understand them, and however, talking about the solution of the problems, we are going to be solving solution of the problems in chapter 6, which is from the book Process Dynamics and Control, and we are going to solve really pretty good number of problems in that. Okay, so going to here, so this is what we are going to take, and let's start. Starting the first method that you want to cover here. And as I'm starting the first method, I just want to remind you by some idea that we had from last time. And what did you say from last time? We said that we have approximation methods, and if we want to apply approximation methods, we do apply them to higher order systems, right? So this approximation of higher order systems. However, if I have a transfer function in a higher order system, I have different methods to deal with the transfer function. So I have the Skogstad method, Taylor series method, and the pad approximation. And all of these methods are good for us to get a good approximated transfer function to a first order plus time delay or a second order plus time delay. However, if I have an experiment, okay, so this is like, I'm talking about a figure. Here I'm talking about a figure, and I mean a figure or an experiment, right? Because you're getting this figure from an experiment. And getting it from an experiment, this is what I get, for example. So if I get something which looks like that, a smooth curve, it's either a first order. I don't mean that it is a first order. It looks like a first order, or a first order plus time delay, or it looks like a second order, or a second order plus time delay. So if it is of any higher order system, I can approximate it to FOPTD, that is first order plus time delay, or second order plus time delay. Great. Now, if I have something that is smooth, in that case, I have several methods that I can use. There are more methods, but we are going to stick ourselves to these methods. Maybe if we have time, we can take more. So we have the SNK method. However, the SNK method is good enough to get the fit for first order plus time delay. Is there also for a second order plus time delay? Yes, we can have. But we are dealing in this course just to fit the first order plus time delay using the SNK method. And regarding Smith method, yes, we can use Smith method to fit a second order plus time delay to this process here. However, if you ask me Smith method, can we use it to fit a first order plus time delay? I would say no. Okay, the answer is no. Okay, so if I ask you the question to fit a first order plus time delay, you will use SNK method. Or you could use the slope-intercept method, or you could use the initial slope method. But you will not use the Smith method, which is for second order plus time delay. If you have something which is oscillatory under damp process, then you can use the damping method, or you can use the Smith method. So the Smith method, we can use it for the smooth and under damp processes. So based on that, what we have, we are going to start with our first method, and our first method that we're going to deal with here is the the initial slope method. Okay, so here I'm trying to use the initial slope method. Okay, so it's one of the simplest ones that I can use here. So if I have a plot of the response, so what do I have? I have a plot of the response. So I have an experiment or a figure, and by that I want to deal with it. If the process of interest can be approximated by first or second order linear model, the model parameters obtained by inspection of the process reaction curve. What I want to say here, we can get a first order model, not a second order. And where's the concept? The concept is that if we have something like that, we already know that if I have a step input to a first order, I'm going to have something that looks like that, okay? And by this, I could have y over km, which is equal to 1 minus e to the power minus t over tau. And then I'm going to take the derivative of both sides, and taking the derivative of this part, the first part here, the derivative of the first part is at, so the derivative of the first part at t is equal to 0, okay, at t is equal to 0, is equal to derivative of 1 is 0, and derivative of e to the power minus tau, actually it is minus into minus, so it's t over tau, okay, so it is t over tau into e to the power minus t over tau. And since we are talking about sorry, it is not t over tau, it's 1 over tau, okay, because we are taking the derivative of t over tau, so it's 1 over tau. And since t is equal to 0, this term will drop to 0. So what do I will have? I will have this equation here, okay, I'll have this equation here. So my exponential term drops, and this is what I have. So what I'm saying that at t is equal to 0, that means at the initial slope, okay, the initial slope. So this is what I have. And what is y over km? We can make some kind of a thing here. So we already know what's the value of k. K is delta u over delta y over delta u, which is change of output or the change of input. And k is equal to delta y over delta u, which is the step input, which is m. In this case, what we are trying to say, we are trying to say that delta y is equal to km. Okay, so the change of the output is equal to km, and we already know that the change of the output is equal to km. So in this case, we can have a good relationship that we can use here. So what we are trying to say again, we are trying to say that the initial slope is equal to 1 over tau. The initial slope is equal to 1 over tau. Again, what we are trying to find, we are trying to find an approximated model which looks like a first order, okay? So we are trying to approximate a model which looks like a first order. What do we need to find? We need to find k and tau. How to find k? K is change of the output over the change of the input. How to find tau? To find tau, we need to find the initial slope, right? We need to find the initial slope. And if we find the initial slope, okay, tau is equal to 1 over the d over dt, which is the derivative of y over km. So that is taking 1 over the slope. 1 over the slope. So what do we have here? You can see that I already have my tau. So I can get here tau, and I can obtain my k. Okay, and by this I'm going to obtain my approximated first order. We don't know our system, okay? My system, which looks like that, okay, which looks like that. If I have something like that, I don't know exactly, I'm not sure exactly, is this a second or a third or a fourth order? Definitely, if I have something that is going a little to the right here, it is a higher order system, second, third, fourth order, okay? And if you want to calculate using the slope-intercept method, it is difficult to apply it here because we have the slope which is not really representing of how does it go out from here. And actually, if you're going to calculate the slope-intercept method starting from here, yes, that could be accurate to give you this trend, but it will not give you the initial trend here. And to get the initial trend, what do you need to do? You just need to say that this looks like a time delay, okay? So you will have a time delay, and then you're going to add a time delay term, okay? I hope you got it. Okay, I hope you got it. But if you didn't get it, okay, I'll try to show it to you within our explanation here. So again, what did we do? We found the initial slope. We want to fit a first order plus time delay using what? Using the initial slope method. Using the initial slope method. And the initial slope, that means the first two values, which is like at t is equal to 0 and the next value, okay, and the next value will give me the initial slope, okay. And having a system which looks like that, definitely this initial slope that I have here, it is giving me a good trend, and by doing what I'm trying to do, fit here to find k and tau. Okay, why I want to find k and tau? Of course, I want to find k and tau because it is my approximated first order system, and so I will have an accurate system that represents the figure here. Okay, so this figure can be represented as that. But if I have a figure, that looks a little bit to the right here, which is like an S shape, and this S shape means what? It means that I have a higher order system. And having something like that, if I take the initial slope here, that will not be an accurate, and it will not get the most of the trend of this figure. So what do we consider? We are going to consider, if I want to apply this method, okay, I'm going to consider like a slope here. Okay, and it's like I'm trying to get what? I'm trying to get the slope of the most of the points here, and by getting the slope, I'm going to take the first 2 points within the slope, and by that I'm going to apply back. This is like the initial slope, and then I'm going to take a time delay here. So this is the initial slope. This is like the initial slope, and this is the time delay that I would have. And in this case, I will fit a model which will look like k over tau s plus 1 over e to the power minus theta s. Okay, so these like are the two ways of trying to apply the initial slope method. And by the way, the one which is usually applied is this one, and then there is another method. Rather than doing this method, there's another method, we call it Slope-Intercept Method, which will help us to do this kind of fit better than the way that I'm trying to explain here. Okay, so you will depend mainly on this idea, but I'm telling you that you can apply it also with a different idea. And how does that apply? Okay, how does that apply now? I mean, just to get an idea. So you have a figure here. You apply the initial slope method, which means I'm going to take the first two values and just take the slope. And finding the slope, I'm going to find tau, which is equal to 1 divided by slope. And of course, k is equal to change of y over change of output over change of input. And khalas. And we have our system here. But what about if we have a table? A table, for example, I have changed, and the time is changing. I had made a step input, and when I made a step input, the concentration, for example, or the temperature, let me say the temperature was changing. It was like 20 degrees, and then it became 20.1, 20.2, 20.4, 20.7, and so on. Okay, and it could be faster than that, and so on. So we have a data here, right? We have data. So what is the initial slope? The initial slope is taking the first two values, and finding that slope here. And the slope here in this case is going to be like 20.1 minus 20 divided by 2 minus 1, and you're going to get 0.1 over 1, which is equal to 0.1. So this is like the initial slope. Even though that, if you just can remember, that this is accurate, this is some kind of an accurate, but if you can remember, the initial slope was y over km. Okay, and actually we can take it as y prime over km as well. Okay, and to get something that is really better, you need to take the temperature minus the steady state value. Okay, and then you divide it by km, and by that you have y over km, and then you can take the derivative. Okay, and by that you have the exact value without any problem. But through experience, I can see that this is applicable. But just to make sure that you're on the safe side, always go through what is obtained from the equation. Okay, so that is the initial slope method. Okay, so going back to the initial slope method, we finished that. Now, instead of going to the idea just for the initial slope method, we want to apply the slope-intercept method. Okay, slope-intercept method. And again, when I apply the slope-intercept method, I can have a figure which looks like that, and I can have another figure which looks like that, and we are going to see that in the next slide. Okay, so I'm going to have the slope which goes like that, as you can see. Okay, this is the slope. And in this case, the slope starts from the beginning, okay, because this is like an exactly first order system. But in this case, we need to look at the inflection point. And looking at the inflection point is not easy, because it is the inflection point in which we have a negative, not a negative slope, that the slope is changing its direction. And as you can see, that's changing direction here. So somewhere the inflection point is here, and then you're going to have your slope intercept. Okay, this is a slope, and it's intercepting here, and it is intercepting here. Going back to this figure here, so it is intercepting here, and it's intercepting there. And as it is intercepting here, it's like my time delay is equal to 0. So there's like this, the figure is starting exactly at 0. However, here I have a time delay, and I need to calculate that time delay. Okay, and from this inflection point till the point here of the second inflection, sorry, not inflection point, the interception point, to the second interception point. So this is called tau. It is exactly as here. From this point, the interception and the interception point, we have what? We do have tau. We do have tau. And we already can recall that our tau is 63.2%. It is 63.2%. And actually our tau of 63.2% is will give me an accurate value, considering that it is a first order and it's starting from here. However, if it's starting from here, we need to consider the 63.2%. However, I need to not consider time delay, because then I'm going to have an error. And we are going to take examples of that. Okay, so if you can remember, how did I get the 63.2%? If you just can remember, like y is equal to km into 1 minus e to the power minus t over tau. And when we said that if you're going to substitute t as 1 tau, okay, when t is equal to 1 tau, okay, and this is what we're trying to get, when t is 1 tau, and we have 2 tau, 3 tau, 4 tau, and 5 tau, we get about the steady state, new steady state value, right? And that is at 5 tau, but at 1 tau, if you substitute t, this will be km into 1 e to the power minus tau, which is t into tau, over the tau value. That is e to the power minus 1. 1 minus e to the power minus 1 is 0.632 km. Okay, and this is the place where we obtained that we said that this y prime at t is equal to tau, we are going to get what? We are going to get 0.632 km. We are going to get 6.632 km. And here we are plotting y over km, so it's like y over km. We are going to obtain what? 0.632 exactly, and this is the 0.632 exactly. Okay, so this is the way of how you can get the value of the slope-intercept method. So just to conclude that, or summarize what I'm saying, for this first order plus time delay model, we know the following. Okay, so we need to fit a first order plus time delay. So this is our aim. We want to fit a first order plus time delay to this response or to this response. Okay, these two different responses. So what do? We need to note the following. The response attains 63% of its final response, which is equal to what? It is equal to tau plus theta. And theta here is the time delay. Okay, so in this case, the first figure here, I have the time delay is equal to 0. So my tau obtained, my t is equal to tau plus the theta, which is 0. So my t is equal to tau. However, in the second case, it is going to be different, because my 0.632% is like I'm considering that I have tau plus theta. So I need to remove the tau, the TD, so that I can get purely my tau, to get my pure tau. Okay, so tau is equal to t minus theta, right? Tau is equal to t, that is at 63.2%, minus theta. In my first example, theta was equal to 0, and in my second example, there is a value of theta. Okay, so that is the equation that we're going to be using. The line drawn to the response at the maximum slope intercepts with y of equal to km is equal to 1. And this is something else. Where is my second intercept? It intercepts at my new steady state value. Okay, it intercepts where? At my new steady state value. Okay, so please consider this, because many people do confuse this. Okay, so the line drawn to the tangent to the response at maximum slope, t is equal to theta, intersects with y over km is equal to one line at t is equal to theta, tau plus theta. If you didn't understand this is just drawing the line, which is tangent, and finding the two intercepts. Okay, so intersects or intercepts. Okay, and it intercepts where? Up here and down here, and then you're going to take the tau. In this case, it intercepts here and intercepts here. So tau is between the two intercepted points. Okay, it is between two intercepted points. The step response is essentially completed at t is equal to 5 tau, and we already said that. So it's a good assumption. We can say that settling time is equal to 5 tau, even though that it enters maybe before that. Okay, so again, this is for the second response. So considering that this is the inflection point, that I have here. So I have two intercepts. This is my first intercept, and this is the second intercept value. And between these two intercepted values, I have tau. Okay, between these two intercepted values, I have tau. And if I have t is equal to, if you can remember, the t is 63 t, the whole t. Okay, so that is tau, and that is theta. And considering the t 63.2%, so here if I take my 63.2% of km, I would guess that it will be somewhere like here, and then it will intercept here. Actually, it will not be exactly, and from my experience, this 63.2% it will give you a different approximation. This will give me a different approximation. It will give a different approximation than the normal slope-intercept, the slope-intercept method. And the reason of that, there are two different methods, but it should have the same basis. But the thing is that you can never get exactly the inflection point. Okay, this inflection point is not easy to obtain, so that you can get a tangent line that is exactly going through it and tangent to the line. So that is not easy to do, and this is why sometimes you will have little difference in tau. So tau using this, that or that, okay, could be different. Hopefully you got what do we mean, and we need to solve problems with that so that we can be able to understand it. Okay, and we are going to solve problems, don't worry about it. Okay, so that was the slope-intercept method that I have just explained. So we finished the initial slope method, and as you have seen, the initial slope method is either we have an experiment of data, or we have an experiment that is represented in a figure. We can use the initial slope method. The initial slope method, we already explained the initial slope method, okay, and then we have also the slope-intercept method, and the slope-intercept method we already explained that. And now we are going to come to the third method, which is the Sanderson and the Krishnaswamy's method, in which I abbreviate this as SNK method. Okay, and the method here is very intelligent in the way that it avoids using the point of inflection, right? As I said, that could be a problem. So to avoid this point of inflection, construction entirely to estimate the time delay. And in that, what it is going to be, I just need to calculate. We have two equations for the SNK method. So this is the SNK method, and these equations are going to be given to you in the exam. So you have the value. This is how to find theta, and this is how to find tau. So we know how to find theta, we know how to find tau. However, what do I need to how can I find theta and tau? Again, why do you want to find theta and tau? Because we want to fit a first order plus time delay. And if you want to fit a first order plus time delay, this is the standard method of the first order plus time delay. What are the parameters that you need to find? You need to find k, theta, tau, and theta. How to find k? K is the change of the output over the change of the input. This is similar for all methods, okay? K. How to find tau? Now I have an equation of how to find tau. How to find theta? Now I have an equation of how to find theta. So I can find tau and theta using the equation. What do I need to know to find theta and tau for the SNK method? I need to find T1 and T2. Okay, how to find T1? T1 is 35.3% of Km. What is T2? T2 is 85.3% of Km. Okay, and by that I can calculate theta and tau. And the question here, how can I know the 35.3% and 85.3% of Km? Okay, just to know how do we do this, it's exactly like 63.2%, right? But just consider this system here, and that was my response. That was my response. And considering the response, for example, this was the temperature changing with time. And having this response, I'm just going to put some numbers so that it becomes more interesting. So like this is 0, 10, 20, 30, 40, 50, 60, and I would consider this like goes to value 60, okay? So I have here, it goes from 0 to 60, and I think so I can apply now many methods in my head, but let me just put the numbers here. This is like one, it is like 1, 10, instead of saying 1, I'll say 10 because it just makes more sense, and this is why I was just thinking. So this is like 10 seconds, 20 seconds, 30 seconds, okay, 40, 50, 60, I'm not sure that they are very equal, 70, okay, just as please make them more accurate, and 80. Actually I had a ruler here, okay, no worries, we are just there. Okay, so if I have something that looks like that, so let's apply now the SNK method, okay? And then I'm going to apply the slope-intercept method. I think so it's a good idea to do this. Okay, so applying the SNK method, we need to find T1 and T2. So what is T1? T1 is at 35.3% of Km. What is T2? T2 is at 85.3% of Km. Okay, so that is T1 and T2. And I'll tell you how to calculate it, and I'll tell you what is the common mistake that happens in the exam. Okay, so what is T1? T1 is 35.3% of Km. So what do I have here? I have from 0 to 60. This is how it changes. So this is how we calculate T1, okay? First, we are going to say 35.3% multiplied by the difference 60 minus 0. So that is 60 minus 0. 60 minus 0 plus the initial value that was here, which is 0. Of course, we already had 0, so it's just by luck it became only 0. But it could have been a different value here, okay? So multiplying this, 0.353% multiplied by 60, now we just can't get it directly, so that will be 21.18, okay? And going to 21.8, now this is not T, and this is the common mistake that we have. This is the T1 at that value. This is the T1 at that value. So this is the whole Km, right? This is the whole Km. So what is this? Is the 35.3% of Km. So what is the value of T1? The value of T1 will be like that. So this is 21.8. So you will go to 21.8. So I'll draw this in red. This is like 21.8 going to this value here, and then we go down. I'm just trying to take an approximate thing. So and then I say that is 30 seconds, okay? I know that one is not exactly done there. Okay, so that is equal to 30 seconds. So that is T. So T should be in seconds, right? Or in time dimension, time units. Okay, great. Now, what will be T2? T2 will be at 85.3%. So that is like 0.853 into 60 minus 0 plus 0. And that will be, the answer will be for that is equal to 51.18. And what will be the answer for this case? I'm going to go to 851.18, and my 51.18 is somewhere here. Okay, and then I'm going to go down there, which is like 40. Okay, I'm just trying to take whole numbers just for the sake of calculations. So this is T1 and T2, and now that I have T1 and T2, all of what I need is to substitute. Okay, and the substitution here, I'm going to take these two equations. Theta is equal to 1.3 T1 minus 0.29 T2. So theta is equal to 1.3 to 1 minus 0.29 T2, which is 1.3 multiplied by 30 minus 0.29 multiplied by 40. And the answer will be 1.3 multiplied by 30 minus 0.29 multiplied by 40. This is equal to 27.4. 27.4. Okay, and you can see that how big is that time delay, and the reason is that if you just recall of what I have taken before, is that it is like taking the slope, and the slope here is something like that, and it's taking this whole part as time delay. Okay, of course this is a different method, but I'm just talking about how it is calculated, considering that my figure is accurate as well. Okay, so let's continue with that. Okay, so continuing how to calculate tau is equal to 0.67 to T2 minus T1. So 0.67 into T2 minus T1, and that is equal to 0.67 into T2, which is 40 minus 30, and that is 10, so that would be 6.7. So my tau here will be 6.7, and I think so that the numbers look like it should be the other way around, but it looks like we have a big time delay, and my tau constant is and actually my tau constant looks like 6.7 because I had a very sharp change here. It just goes up, really spiking up, and maybe that is the reason that it reaches 63.2% really quickly there. Okay, so if I obtain theta and tau, and now I need just to find the value of k. I did not put a question here, but if I say that if I had a step input, for example, of changing the power from 0.1 kilowatts, okay, to 0.1 is very low. I mean, I would say like 20 to 30 kilowatts, okay. So I'm changing this value. So my input here is what? Is 30 minus 20, which is equal to 10. So that is the change of the input, and the change of the output, it changes from 0 to 60. So the change is 60. And if I want to calculate k in this regard, it will be change of output over change of input, which is equal to 60 over 10 is equal to 6. And here I have all my values, which is the k, tau, and theta, and I then can put my first order plus time delay, which is k6 over tau s, which is 6.7 s plus 1, e to the power minus theta s, which is minus 27.4 s. And that is my fitted, first order plus time delay. Okay, I hope this was clear of how we are using the SNK method. Now, considering that I don't want to use SNK method, okay, I want to use the slope-intercept method. And using the slope-intercept method, I will try to use now the flash color here. What is 63.2% here? 63.2%, again, it is 0.632 multiplied by 60 minus 0 plus 0. So the answer here will be 37.92. And considering 37.92, which is somewhere here, right? Somewhere here, and then you go down there, you can see that I have here my 37.92 goes to a time like 32, okay, 32. And if you consider that that 63.2% is the t plus time delay, and how to get that? If we do our slope thing here, okay, so the time delay will be about 19, and so the time delay that I have here is about 19. Okay, so the time delay using that, this is like the 63.2% method, the slope-intercept method, right? I'm using like, I'm mixing up between the 63.2% and the slope method, right? It's easier to use the slope-intercept without the 63.2. So just applying 63.2% method, and then I'm going to talk about like the slope-intercept method, because they are like two different kinds of method, even that they have the same basis. Okay, so just considering that this is what I have here, now I'm trying to do the 63.2% method, and in doing this, what I have here, the 63.2% method tells me that tau, okay, is equal to tau, the t, let me say t is equal to 31, and the theta is equal to 19, so the tau will be something like 12. Okay, so now what are the values? 19 and 12. They are different from the SNK method. Yes, they are different. Okay, what about the slope-intercept method? If you talk about the slope-intercept method, actually if you take the intercept here the intercept here, it is different. It's different from the 63.2%. And so it will give me a different value, like 38 in this case. So what I will have as t is equal to 38, right? I will have 38, and my theta is 19, so my tau is equal to 19. So in this case, if you can see that I also have a different theta, the theta will be like the same, but I'll have different tau, a different tau. And these are also different from what? They are different from the values that we had obtained, using the SNK method. So as you can see that, like all the methods that we have here, it is giving me something little different from the rest. And this is normal. Okay, because we are doing a lot of approximations. The figure is not that accurate, but I'm trying just to deliver the understanding of what you're trying to do here. Okay, so that is the SNK method. What about if there are some other methods? Yes, there are other methods, and one of those methods is what we call the Smith method. Where is it? Yeah, here. I was just searching for that. Okay, it's the Smith method. Before going to the Smith method, there is some kind of an approximation that is used, and this approximation says that if you have that, actually this is using a transfer function. So I think so that I may have included here, but I shouldn't have included that here. I should have included that somewhere else. Okay, just to consider this. So this this method, what does it say? This is not applied for a figure, by the way. Okay, it's not applied for a figure, but it just gives you an idea that if this is like 10s plus 1 into s plus 1, I just can consider that is this s plus 1 negligible in comparison to that 10s plus 1. If it's about 10 times, this is somehow negligible. If it's also 0.1 s plus 1, it's definitely going to be negligible. So what we are trying to say here, you can sometimes ignore the second part of it, and this is like an approximation. Okay, so this is the concept of it, that you can do things like that. And what does that all mean? It means that if you have a very fast response, like for example you're using an instrument, a sensor, and this sensor is really fast, okay, and because it is fast, the tau is small, and because it is small, if you put that in the S-plane, okay, it's like you're having in 0.1 seconds, okay, in 0.1 seconds it is giving you the answer. And if you equal to this to 0, the denominator equal to 0, the S is going to be something like minus 10. It's going to be somewhere here. But if you take a slow process like 10s plus 1, and that is multiplied by 0.1 s plus 1. In this case, this 10s plus 1 is, the answer is 10s plus 1 is equal to 0, s is equal to minus 0.1. So that is really very close. So this dominant pole, this is like dominant pole, that dominant pole will ignore, it's not will ignore, that pole will be negligible in comparison to that dominant pole. Okay, and then what you're going to do, you're going to cancel out this term. And this is the reason that sometimes if we have sensors, we do not consider the transfer function of those sensors. We consider the transfer function of those sensors as 1. Why? Because k is always 1 for a sensor, and now the denominator of that sensor will also be 1 because it will be very fast, and that means that it's negligible to the other transfer function of the system. Okay, so this is why you always hear that Gm is equal to 1, the transfer function is equal to 1. Actually it is 1 over some kind of a very fast response, and in comparison this drops out and then it becomes like 1. Okay, so that was something to do with the transfer function that came in the middle of our explanations. Okay, so that what do we have? We have a Smith method here, and in the Smith method you always remember what I want to fit. I want to fit a second order plus time delay. Okay, so if I'm requested to fit a second order plus time delay, I will not use the slope intercept, I will not use the initial slope, I will not use SNK method that is used for first order fit. I'm going to use what? I'm going to use the second order plus time delay. Now, I'm talking all about what? I'm talking about the methods that you really need to fit if you have smooth processes, right? And for here, this could be applied to smooth or oscillatory processes, right? This can be applied to both. Okay, so what do we have here? We need to find K, we need to find theta, we need to find tau, we need to find xi. How to find K? Change of output over change of input. That's as simple as it is. How to find these values? If you remember, the damping method has equations how to find these values. If you have that the settling time, you have an equation. If you have the overshoot, you have an equation. So the damping method will help us to find these values. So this is found by the overshoot or the decay ratio, all right? And this is found by knowing the settling time or the peak time, the time for the first peak or the period, okay? And theta is just by looking at the figure or the data, you can know theta. Now, this is if we are talking about the damping method. Now we are not talking about the damping method. We are talking about what? We are talking about the Smith method. In the Smith method, K is always delta Y over delta U. And theta is going to be obtained like from the graph just by like approximating it through your eyes. And that's not easy because we need to know that should be a really delay method and not the part of the S shape. Okay, it's like a part of the S shape is something like that. Okay, but if you have something that is like that and then it goes like that, so this is part of the S shape that will be considered. But from here till here, that is definitely a time delay, and then you're going to be considering this e from minus theta s. Okay, so what we need to find now, other than the theta and the K, we need to find tau and xi. How to find tau and xi? We need T20 and T60. Again, 20% of Km and 60% of Km. If you determine T20 and T60 from the figure, okay, if you determine T20 T60 from the figure, all what you need to know now, use figure 7.7 to find T60 and over tau, and by that we can find tau, and to find xi. And if you find T60 over tau, of course you're going to find tau, and xi is already identified. Can we see the figure? Yes, this is the figure that you have. And considering that we have the T20 over T60, I don't know what is T20 over 60, but just assuming, for example, we obtain T20 is equal to 5 minutes, okay? And for example, we obtained T60 to be, for example, 8 minutes. Okay, I'm just taking an example here that this is like T20 and T60. Okay, 8 minutes look very fast, so I'm going to take like 12 minutes, okay, because this is T60, right? Just to give a flavor of its accuracy. So what do we have here? T20 over T60 is equal to 5 divided by 12, which is 0.417, okay? It's about 0.42. So going to 0.42 somewhere here, for example. So this is like 0.42. And what do we have here? We can find the T60 over tau, which is what we can see here. This is the T60 over tau axis, and this is the axis for xi. So this T60 over tau, we are going to go to the left. So we are going to go from 0.42 to the left, and we are going to find that T60 over tau is 2. Okay, so my T60 over tau is equal to 2, which means tau is equal to T60 divided by 2, and my T60 was 12 minutes, so 12 divided by 2, this will be 6 minutes. Okay, so I found tau. And how to find xi? I will go little up there and find that it is about 1.0 something, right? Oops. Okay, so I have that this will be like that. I mean, it's very close. But it is above 1, okay? It is like above 1. So let me say, for example, that this xi is about 1.05, okay? And this is greater than 1. So it will give me an idea that it is smooth, right? It's smooth, not oscillatory. It is overdamped. Over 1, overdamped, okay? So it's an overdamped process. So I already found tau and I already found xi. What I need to do, k, which is change of output or a change of input, found. Tau square s squared, tau is found. 2x xi tau s, we found xi and tau, plus 1. So we can substitute everything here to find my second order, approximated second order system. How did we do this? Just by knowing what is T20 and T60. So this is using the Smith method. That is using the Smith method. And going to our final method, which is fitting an integrator model, in which I don't really bring that in the exam a lot, because and that's why in my big figure that I showed you, if you remember my big figure, where is it? Okay, it's still up here. Oh my god, I have taken a lot. Okay, so that is my big figure that I usually explain. So my approximate methods, I have this method if I have a transfer function, and I have also the approximation if I have the smooth overdamped processes or the underdamped processes. So what we have taken so far, we have taken the SNK method, the Smith method, which is also applicable here. We have taken the slope-intercept method and the initial slope method. I know that we have like the integrator method here, in which I usually do not include it. I say that this is enough for you to know these kind of methods. But I'm going to take that as well so that you can gain from it. And the damping method, we already had taken that before using the overshoot, decay ratio, and all the other methods here, okay? We have taken that previously. So what are we left with? The integrator method. So again, y is equal to km into 1 minus e to the power minus t over tau. When do you have this? If you have a step input to a first order process. If you have a step input to a first order process, this is my output. And if this is my output, now just using the Taylor series, if you remember Taylor series, it was like e to the power minus theta s is equal to 1 minus theta s, taking only the two first terms. So if I have e to the power minus t over tau, that will be 1 minus t over tau. So if I substitute here e to the power minus t over tau, I'm going to substitute 1 minus t over tau. So here's like 1 minus t over tau. I'm going to have the ones is going to cancel out. So km is going to be multiplied by t over tau. So it's km t over tau. Okay, did you see that? Km with t over tau. And this, of course, minus would be 1 minus 1, and that minus will make this positive. Will make that positive. So what I'm going to have? I'm going to have 1 minus 1 and 1 plus minus minus plus t over tau. So the answer is km over tau t. And if you want to look at it with the time delay, it's going to be km over tau with that time delay thing if we have. This is the way how it's represented in the time, in the t domain. So this is the approximate method, but we are not going to take problems with that. We're going to concentrate more on the problems that the ones I had explained. So that's it. That's what we have for chapter number 6. And we are going to be solving methods before we get into the chapter number 7. So here where chapter number 7 starts, and we are going to solve chapter number 6. After we solve chapter number 6, you just need to know that there are other methods that are used, and I'm going to explain these methods as well. However, these methods need intensive calculations. Intensive calculations, that means it needs a lot of calculations that takes a lot amount of time. So it's different to bring those usually in exam. But you need to have an idea about it, and we're going to take these in our next session. So we already finished the approximation methods. We are going to solve chapter 6 next time. And after solving chapter 6, we are going to take the other methods. It's considered like also some kind of approximation methods, or it is like more than an approximation, because it's using a finite difference approximation as really accurate and very powerful technique. And the MPC, the model predictive controller, uses the discretization method, which is part of what we are going to explain here. Other than that, we are left with a state space modeling, and we're also going to take the state space modeling, and that is also going to be one lecture. And we are also left with two kind of processes called or at least one of them, the interacting and the non-interacting processes, just to understand the concept of that. We already have taken it, but we did not introduce these terminologies, and we are going to introduce these terminologies. All then, by that time, we have finished our approximation methods, and that is my approximation method. And hopefully you have gained a lot from what we have taken. And all the best, and see you in our next lecture. Masna.